Hello everyone, welcome to the channel Statistica. Now in this lecture we will do elementary operations. Elementary operations, or you can say elementary transformation, transformation. Okay, so we have been using elementary transformation for reducing a matrix into its echelon form. Okay, for reducing a matrix into any form, into echelon form, into normal form, into canonical form, we always use these elementary operations. Okay, so let's just see these. What are these operations? That when we interchange any two rows or columns, that is Eij. Okay, this is my operation of interchanging any two rows or columns, that is Ei to Ej. Okay, this is what interchanging any two rows or columns of a matrix. Okay, now the second one is the multiplication of elements of any row or column by a non-zero scalar, and this transformation is represented as Eik. That means we are applying Ei to Kei. Okay, this is what? This is multiplication of elements of any row or column by a non-zero scalar, and here k is the scalar. Okay, and the third one is the addition of elements of any row or column, the scalar multiples of the corresponding elements of any other row or column. That means we are applying Eijk here. Okay, that means Ej, and we are doing Kei plus Kj. Sorry, Ej. Okay, so this is the transformation here. This is what? This is addition of elements of any row or column, the scalar multiple of corresponding elements of any other row or column. Okay, so these are the three type of transformation here, that multiple of scalar interchanging the two rows, and the third one is addition of elements and the scalar multiple of to the corresponding elements of any other row or column. Okay, now what are these elementary matrices? E matrix, or you can say elementary matrix. The elementary matrix are actually obtained from a unit matrix, or you can say identity matrix. Okay, these are obtained by identity matrix by subjecting it to any single elementary transformation. When we apply any single E transformation on the unit matrix, we obtain our elementary matrix. Okay, so let's just see it like this, that my identity matrix of 3 cross 3. Okay, this is my identity matrix of 3 cross 3. Okay, now I am applying the transformation as interchanging R1 to R2. Okay, so by applying this transformation, we will get our matrix as 0, 1, 0, 1, 0, 0, and 0, 0, 1. Okay, so this is my corresponding what? This is my corresponding E12 matrix. Okay, E12 elementary matrix of the single row transformation, which is the transformation I have applied. It is R1 to R2. Okay, similarly you can get another elementary matrix, which is multiplication of any scalars. Okay, so if in this identity matrix we'll do in R1 2R1. Okay, then the corresponding matrix after multiplication of the scalar 2 will be 2 0 0 0 1 0 and 0 0 1. Okay, so this is my another elementary matrix. Another elementary matrix. So what are elementary matrices are? These matrices are obtained from a unit matrix by any single elementary transformation. So we have to apply just a single transformation on a unit matrix. Okay. So we have seen that the elementary matrix are actually obtained by the identity matrix, and we know that the inverse of the identity matrix is actually identity. Okay. Okay, so for checking that, let's just check that elementary operations as EIK and EIJK, whether these operations possess an inverse or not. Okay, so for checking that whether these possess an inverse or not, we apply the determinant rule. If the determinant of these EIJ is equals to 0, then they are singular and they didn't possess an inverse. And if the determinant of these is not equals to 0, that means they possess an inverse and the matrices are non-singular. Okay, so for checking the determinant of the first one, which is determinant of EIJ. Okay, and as I have said here, that this EIJ is obtained by interchanging any two rows. Any two rows. So when I interchange the two rows, the determinant of identity. What is the determinant of this identity is 1. Okay, and when we interchange the two rows, the determinant of this matrix, that is EIJ. Okay, here it is E12. Okay, so when we take the determinant of this, and it will be minus of 1. Okay, you can just check it by taking out the determinant. So the determinant of minus of EIJ is actually minus of identity, and that is equals to minus of 1, and this minus of 1 is not equals to 0. So from this we got an important result that, as a result of interchange of any two rows of columns. Okay, as a result of when we interchange any two rows or columns, the value of determinant remains same in magnitude. The value of determinant remains same in magnitude, but changes in sign. Changes in sign. Okay, so this is the result we got by this, that I have said the determinant of the identity matrix is 1, and when we interchange the rows of the identity matrix, that is E12, the determinant of this is minus 1. The magnitude remains the same, that is 1 here and 1 is also here, but here it is a plus sign and here it is a minus sign. So the interchange of any two rows or columns of the matrices uh, cause the determinant value remains same in magnitude but changes in sign. Okay, and this for checking the determinant of the second one, that is determinant of EIK. Okay, what is the determinant of EIK? That has to be equals to K into identity. Okay, you can see it like this, that in the scalar multiple I can write it as the determinant of this matrix. We have seen that the determinant of the identity is 1. So if you find out the determinant of this matrix, and it will be equals to 2 into determinant of identity, that is 2. Okay, so from here we have the determinant here as K. Okay, which is not equals to 0 because K here is the scalar. Okay, now we'll look for the another determinant, which is determinant of EIJK. EIJK. Okay, so when we take out the determinant of this EIJK, we got determinant of identity. Okay, you can check it like we have done for the earlier two precisions. Determinant of identity is 1, that is not equals to 0. And from this third one, we got an important result that the value of determinant remains unchanged if to the data if to the elements of any row we add scalar multiples of the corresponding elements of any other row. Okay, so here the determinant's value is unchanged. Okay, so from this we can see that the each elementary transformation is non-singular, as its determinant is not equals to 0. So each transformation is non-singular. So as these are non-singular, so they possess an inverse. Okay, so now we look to the inverse of these elementary transformation. Okay, so now let's see the inverses of these elementary matrices. Okay, inverses of elementary matrices. So our first inverse is Eij inverse. Okay. So we got Eij from a unit matrix. Okay, let's just take an example that I have this unit matrix of 1 0 0 0 1 0 0 0 1. Okay, this is my unit matrix here. Okay, identity matrix. Now, if we perform E operation on Eij, that is Eij E12. Okay, now interchanging the two rows, that will be 0 1 0 1 0 0 and 0 0 0 1 0 0 1. Okay, so this is my E12. Now if I want to find the inverse of this E12 matrix, then what do I have to do? That if we perform same E operation Eij, we again get a unit matrix. Okay, now if I again do E12, that is interchanging of this R1 and R2, we will get again 1 0 0 0 1 0 0 0 1, and this is my corresponding unit matrix. Okay, so what do we have done is that we are doing Eij, and when we again apply Eij, we got identity matrix. Okay, so the inverse of Eij inverse is equals to Eij. Okay, now look for the another one. Let's just look at that Eik is inverse. Eik inverse. So we got Eik by the identity matrix if we multiply a scalar to it. Okay. So this is my identity matrix, and if we multiply 2 to it, okay, then this will be the elementary matrix will be 2 0 0 in the first row. We are multiplying the scalar 2 in first row. Okay. 0 0 1. Okay, now for getting the identity matrix again, what do we have to do? We have to divide the first row. In the first row we have applied 2r1. Now what we'll do, in the first row we will do r1 by 2, then we will again gain identity matrix, which is 1 0 0 0 1 0 0 0 1. So what have we done here is that we have Eik, and when we have applied Ei 1 by k, okay, then we got our identity matrix. Okay, now you can do this multiplies this elementary matrix of Ei 1 by k in post, and we can post multiply it and pre multiply it. Like I can write it as Ei 1 by k Eik, and that is also equals to identity. Okay, now from these two we got that Eik inverse. Eik inverse. Okay, what is the inverse of Eik? Is Ei 1 by k. Okay, and you can write it as Eik is inverse. Okay, so this is the inverse of Eik. So now let's just see the third one, which is Eij inverse. Eij inverse. So for finding this inverse, so we are performing Eijk. Okay, in like previously we have done for Eijk and Eij, so we have to apply the transformation of Eij minus k, and we will get our identity matrix. Okay, we will get our identity matrix like this. So what is the inverse of Eijk? The inverse of Eijk is equals to Eij of minus k. Okay, so we have got the corresponding inverses of these E matrices. So you can see that the inverses of these E matrices are also elementary matrices of same type. Okay, like we have for the inverse of the interchanging of any two rows or columns, we have got a R inverse as Eij, which is also interchanging of any two rows or columns. For the scalar multiple, we have also got the inverse as the scalar multiple of the 1 by k, and similarly for the Eijk, we got Eij of minus k. Okay, so from this we got that the inverses of E matrices, inverses of E matrices are also E matrices of same type, same type. Okay, now let E be the elementary matrix. E is the elementary matrix elementary matrix which is required to pre-multiplying a square matrix A for making an elementary row operation on A. Okay, so we are saying that E is my corresponding elementary matrix which is required to pre-multiplying a square matrix A for making it an elementary row operation on A. Okay, so then E transpose, the transpose of this elementary matrix is post multiplying. The transpose of this elementary matrix is post multiplying A for making elementary column operation. Elementary column operation. Okay, so let's just write it clearly that let E be the elementary matrix which is required to pre-multiplying a square matrix A for making an elementary row operation. Okay, this is the E matrix which is required to free multiplying for making an elementary row operation. Then we will have E transpose, the transpose of this matrix, E transpose elementary matrix post multiplying a square matrix A for making elementary column operation. Okay, so for the column operation we apply post multiplication, and for the elementary row operation we apply pre multiplication by the elementary matrix. Okay, so these are actually very important results of these elementary matrices. Okay, let's just note them, that every elementary row or column transformation of a matrix is equivalent to pre or post multiplication with corresponding elementary matrix obtained from unit matrix. Okay, what we are saying is that let's say we have this matrix A. Okay, now we can write it as identity of M into A, and that is also equals to A into identity. Okay, now if we look to the A's of M cross N, A's of M cross N here. Okay, now if we look to the row transformation. Okay, then the row transformation on this matrix A is equals to the same transformation on the identity matrix of M order into A. This is the pre-multiplication with corresponding elementary matrices. This is the set of elementary matrix obtained from obtained from unit matrix. Okay, now for the column transformation, the same column transformation on the matrix A are equals to post multiplication. Okay, A into W of identity of M, N. This is of N order. That is, because there are N columns. Okay, so this will be equals to post multiplication with the corresponding E matrix. Which is obtained from unit matrix. Okay, so this is the important result, that every elementary row or column transformation of a matrix is equivalent to pre-multiplying and post-multiplying with corresponding elementary matrix which is obtained from unit matrix. Okay, now if we look into the multiplication of the two matrices. Okay, so in that case we have that every elementary row or column transformation on the product of two matrices is equivalent to same elementary row or column transformation on prefactor or post factor. Okay, so what are we doing here is, this is my A, which is Aij of m cross n. Okay, and my there is another matrix B, which is Bij of n cross p. Okay, and then the corresponding multiplication of these two matrices is of order m cross p. Okay, now we are saying that every elementary row transformation, if we talk about the row transformation, let's apply row transformation on these matrices AB is equivalent to same elementary row transformation on prefactor. That means if we apply row transformation on the multiplication of these two matrices is equivalent to the same row transformation on the matrix A into the matrix B. Okay, and if we talk about the column transformation into this multiplication of this AB, that means that same column transformation is equivalent to the uh, transformation on the post factor of, that is A into WB, post factor of the matrix. Okay, so what we have done here is, if we apply the transformation on the multiplication of these two matrices AB, if we apply column transformation or either row transformation or column transformation, and that is equivalent to, if we apply row transformation, that is equivalent to the prefactor, say applying same transformation on the prefactor, and if you apply column transformation, that is equivalent to the applying the same transformation into the post factor. Okay, that means if we apply same transformation onto the matrix A, and after applying the transformation we multiply this matrix A into B, we get transformation applied on the matrix multiplication of these two matrices AB. Similarly for the columns. Okay, now another result is, if we perform elementary row and column operation on A. Okay, so this is my matrix A, and on this if we perform elementary row or column operation on A, the order on which these transformations are performed is immaterial. That means we can write this matrix as P A Q and P A Q. Okay, where P is elementary matrices corresponding to row, and Q is elementary matrix says corresponding to column. Okay, so what is this, that if this is my A matrix. Okay, now if we perform the elementary transformation on these matrices, so I can write this matrix into this format, where P is my all the set of elementary row transformation, all the set of elementary matrices corresponding to row transformation, and Q is all the set of elementary matrices of corresponding column transformations. Okay, so if a finite sequence, let's say this is my set S, which is a finite sequence of elementary row operation. So if this finite sequence of elementary row operation is performed on this matrix A, okay, the resulting matrix is, then the resulting matrix is, after applying all the sequence of elementary row operation, we have the matrix as PA. Okay, and what is P? P is the set of all the elementary matrices which are corresponding to the row transformation. Like let's say we have applied the transformation for on the A, which is as EIJ EIK. Okay, so my P will be EIJ into EIK. Okay, so this is my P here. Okay, and what is Q? Similarly for the columns, so Q is the set of all elementary matrices corresponding to the columns. So let's take set S, which is the, let's take set S here, which is the finite sequence of elementary column operation on the matrix A. Okay, then the resulting matrix of all the column operations is Q AQ. Okay, because in the columns we multiply post multiplication, we use post multiplication. So we'll multiply the set of the all elementary matrices Q to the post multiplication of the matrix A. Okay, so this is the elementary matrices corresponding to row and elementary matrices corresponding to column. Okay, now if you look into the basis parts, because this is the elementary transformation and we use elementary transformation in many of the ways, we can find basis too by these elementary transformation by reducing it to the echelon form. Okay, we have been doing this from the very starting actually. Okay, so we use elementary transformation in reducing it to the introduce a matrix into its echelon form. Okay, so for the echelon form, if we look into the basis part, let's say this is the matrix A of m cross n. Okay, and B is the echelon form of this matrix. Echelon form of this matrix A. Okay, now then all the echelon form will be like 1, and there are some elements here, but I'm taking off this like just an example, right? Okay, this is my correct, and these are all zero. There, these all the elements are there are zero here. Okay, so here the non-null rows of the matrix B form basis of row space of A. Okay, what is this? If I reduce a matrix A into its in echelon form, then the non-null rows of B form basis of row space of A. Okay, so let's just consider that if the rank of this A is equals to R. Okay, if the rank of this matrix A is equals to R. Okay, and the corresponding array, which is S1, S2 to Sm, which is the corresponding array for this matrix. Okay, because this is of AM, and it has m rows. Okay, so the corresponding array we are taking as S1, S2 to Sm here of this matrix. Okay, then what will be the basis according to this? Then as the rank of this matrix is R, the S1, S2 to Srth rows of original matrix A, of original matrix A form basis of row space of A, on basis of row space of A. So this is the case when we want to find the basis with respect to the original matrix. Okay, and we can find the basis with respect to its echelon form too. That all the non-null rows of B form basis of row space of A. Okay, now let's look into the form which is a very important form in the linear algebra. Actually, we are going to do reduced forms. So there are reduced forms. So there are basically three types of reduced forms, that is echelon form or canonical form, or it is also said to be the row reduced echelon form, and another one which is normal form. Okay, so these are basically three types of forms here, and when we reduce any matrix, okay, by the use of elementary transformation. Okay, so echelon form of a matrix, this echelon form of a matrix, this is not unique. Echelon form of the matrix is not unique, because we got echelon form by performing elementary transformation, and we can perform many types of elementary transformations for getting our echelon form. Okay, so we it's not sure that that depending on the transformation we are applying, we got different echelon forms. Okay, so the echelon forms are not unique, but the row canonical form, sorry, row canonical form, or you can say row reduced echelon form, or you can say canonical form, these are unique. These are unique. So when we do the canonical form into the deep concept, you will will do this in the next lecture. So at that time you can understand that why these are unique, because of their spatial format, which is similar to the echelon form, but after applying more transformations on the echelon form, we got our canonical form. Okay, and the normal form is also of great use, because it simplifies the matrix representation into a very simple format. Okay, Okay, so let's just see the basics of these echelon form. Then what is echelon form? So basically the echelon form is obtained by Gaussian elimination. It is obtained by Gaussian elimination. Okay, a matrix is said to be in its echelon form if, let's just write it here in a proper format, echelon form. So this is the matrix A, and this matrix A is said to be in its echelon form if it satisfies some properties which are as that all zero rows, all zero rows, if any exist in the matrix, if any are at the bottom of the matrix, are at the bottom of the matrix. Okay, so if there exists any zero row, that should be at the bottom of the matrix. Okay, the second condition is that each first non-zero element, each first non-zero element in a row is on right hand side, right hand side of first non-zero element in preceding row, in preceding row. Okay, so what are we saying here is that each first non-zero element in a row is on right hand side of first non-zero element in preceding row, or you can also say it like that all entries in a column, all entries in a column below a leading entry, below a leading entry are zeros. Okay, so how does this echelon form looks like? This is the matrix A, which is of Aij. Okay, now if we reduce this matrix by applying transformations, okay, then this matrix we reduce to its echelon form like this. Let's say, okay, okay, this is the echelon form here. Okay, and the corresponding elements which are like this, these are my pivot elements. These are what? These are pivot elements. Okay, and this is echelon form. This is echelon form. So what are the conditions for this? That all zero rows, if there exists any zero row, if there exists any zero row, that is any of them, so that should be on the at the bottom of the matrix. Also, if there exists any zero row here, so that should be here. Okay, at the last, at the bottom of the matrix. Okay, and the second condition is that each first non-zero element in a row is on the right hand side of first non-zero element in the preceding row. Okay, so from this here he can, or you can say that all entries in a column below a leading entry are zero. So this is my leading entry here, this is my pivot column here, and all the entries below it in the column are zero. Similarly, here this is my leading entry here, this is my pivot column here, so all the entries below it are zero. Similarly, for this one we have this entry as zero. So this is my echelon form. Okay, so we have been using the elementary transformation on the matrices to reduce it to the echelon form for the simplification purpose, because we have to apply the echelon form in finding the basis, in finding the inverses, in finding the ranks, in the solutions of the linear equation, system of linear equations. Okay, so these in reducing a matrix to its echelon form is actually for the solution purpose, simplification purpose, because we got so many zeros after reducing it to the echelon form. So it is easy to calculate the uh, system of linear equations in at that time. So because we got so many of the zeros, so it has been reducing the equation, it has been reducing the system of linear equations. Okay, so these types of echelon forms are basically of main use in the linear algebra. Now another form we have done is row canonical form. row canonical form or row reduced echelon form, and the other one is normal form. Okay, now these are also very important because the row canonical form is the form which is obtained by the echelon form, which is obtained by echelon form, that is row canonical form, like row canonical form. Okay, so let's just do these two forms in our next lecture, which is row canonical form and normal form, and we'll do some more examples of these forms in our next lecture. Thank you.